If you take a standard carbon chain and replace one of its predictable hydrogen atoms with a highly reactive halogen like chlorine, bromine, or iodine, the entire molecule changes. You've just created a haloalkane. These molecules act as versatile intermediates. Because halogens are easily swapped out for other groups, they allow chemists to assemble the complex carbon skeletons required for modern pharmaceuticals at an industrial scale. Beyond the lab, they are essential to thermodynamics. For decades, haloalkanes like Freon were the primary cooling agents used in nearly every household appliance. However, halogens are aggressive elements. Simply attaching one to a chain produces unpredictable results, because the chemical properties shift based on the exact spot where the halogen lands. To manage this volatility, chemists use a three-tiered sorting algorithm to map molecular structures and predict how they will behave in a reaction. First, we count the halogens, splitting our tree into mono, di, and polyhaloalkanes. While mono and poly are straightforward, dihaloalkanes, with exactly 2 halogens, require checking their placement. If both halogens share the same carbon, it's geminal. On neighboring carbons, it's vicinal. To see the deeper rules of molecular geometry, we're going to follow the mono branch downward into the next tier. Counting atoms is only the first step. The physical network surrounding those atoms is what truly dictates the molecule's reactivity. Moving down the monohaloalkane branch, we identify the anchor carbon, the specific atom that the halogen is directly plugged into. We classify the anchor by connectivity. Attached to one other carbon, it's a primary classification. 2 connections is secondary. 3 is tertiary, where the anchor is surrounded by carbon groups. This physical crowd around the anchor is called steric hindrance. Steric hindrance acts as a physical shield, determining how easily an outside molecule can reach the anchor to trigger a chemical change. The final layer of our algorithm's classification depends entirely on the invisible, underlying geometry of the electron bonds themselves. In the sp3 branch, the anchor uses only single bonds, categorized as alkyl, allylic, or benzylic, based on proximity to double bonds or rings. Conversely, the sp2 branch features an anchor within a double bond, resulting in vinylic or haloaryne classifications. This fundamental geometry locks in the molecule's final identity, completing its profile in the sorting algorithm. Combining halogen count, degree, and hybridization creates a complete structural map. Knowing a molecule's tier 2 degree predicts its reaction pathway, SN1 or SN2. Tier 3 hybridization predicts bond stability, since an sp2 bond is much stronger than an sp3. This system is a predictive tool. It gives scientists the precise vocabulary to control chemical outcomes and design the specialized materials we use every day.